So I want to talk briefly about graph search problems. And so this is kind of a fundamental algorithm challenge. It's something that everybody should know about. And it's something, it's the kind of thing that needs to be in our lingo, right? We should be able to talk about depth first search and breadth first search without thinking too hard about what's going on. And so let me give a very, very informal introduction to how depth first and breadth first search work. And then I'll invite you to go and study for yourself in the book to kind of convince yourselves of why these things operate the way they do. So the basic idea here in a graph search problem is that you start somewhere in the graph and then you come up with a way of just enumerating the vertices in the graph. So you come up with a way of traveling along the edges and searching every single vertex, right? So ideally, now I shouldn't say ideally, right? A graph search is a way of enumerating everything in the graph and of looking in every single one of the vertices in a kind of a methodical way. This is not a shortest path problem. So we're not looking at weights on the edges, and we're not thinking about how do we get somewhere quickly. We're just thinking about how do we enumerate it in a methodical way. And then we'll be able to use these kinds of graph search algorithms to motivate other stuff in the future. But the basic idea is the following. So we'll have two kind of methodologies of enumerating all the vertices in the graph. And the first one is called a depth first search. So this is the depth first search, or I'll call it Dfs. Right? So a DFS basically starts somewhere, and for all these I'll just start here. I'll make this one red. For all of these I'll start on A. And so with depth first search, what we do is we start somewhere and then we start walking, and we keep going further and further and further away from our starting node until we hit a dead end. And further from the starting node doesn't really mean anything, right? You shouldn't think about this graph as being in space. You should just think about further from the starting node means I'm just gonna do the longest line that I can, right? So we'll think a little bit about what that means in a second. But here's an example operation. Well, let me talk about both, and then I'll run both of these searches on this particular graph. So depth first search basically means walk away from start till you get to a dead end, and then you backtrack as little as possible, and then continue, right? So you then backtrack as little as possible, then continue. Okay, so how does DFS work on this graph? Well, let's just run it. And so at each of these points, I'll adopt a rule that says if I have a choice to make about which way to go, I'll break ties, like I'll make that choice alphabetically. So I'm sitting here on A. I have to choose what node to go to next. I'll go to a neighboring node that has the lowest alphabetical name, and so I'll go from A to B. Okay, so in DFS, and I'll just track them down here. In DFS, the first node I visit is B. Okay, so now I've been to B. There's my first edge. And then there's only one way to go that doesn't involve backtracking, and so that takes me down to F. So the next thing is F. Now I have two choices here. I can go to E or I can go to C. Now remember, I want you to make sure you're not thinking about this as a graph in space. So going to E, you know that as a human being looking at the way I've drawn this out, going to E looks like I'm going closer to A. The algorithm doesn't know that. All the algorithm knows is that it has to choose between two nodes to go to next. And it's going to choose the one, like I said a second ago, it'll choose the one with the lower alphanumeric value. So it'll go to C. Okay, so then it has now gotten to C. And so now what depth first search has done is it's kept track of all the nodes that it's been to so far, and it's kept track of them on a stack. Okay, so each time it visits a node, it pushes it onto the stack, and then it says, as soon as it hits a dead end, it starts popping nodes back off the stack. And popping nodes back off the stack is a way of backtracking in a systematic way. So what that means is that once I hit C, I'm at a dead end. So I will pop, I've just pushed C onto the stack. So now I'll pop C back off the stack, which takes me to F, which is the last node or the previous node I pushed onto the stack. So now from F, I do have a choice, right? I have a place I can go, so I'll go to E. Right, so the next place I go after C is E. Now notice down in my list of what I've done here, I'm not keeping track of the fact that I went back to F, because in a sense I didn't go back to F. Algorithmically, all I did was notice that F was on the top of my stack. Right? So I said, what are the remaining neighbors of F that I haven't explored yet? And I noticed, oh, E is a remaining neighbor of F that I have not explored yet. So I'll go to E now. Okay. And so from E now there's only one remaining neighbor that I haven't been to. Right? E has several neighbors. It has F and it has A, but I've been to both of those. So D is the only one left to visit. So there we go. And so then the last node that DFS visits is D. So let me just make sure that it's explicit that we're starting at A in this. So I'm going to explicitly write A there into my list. It looks like it's showing up just fine. And so there's the graph traversal that we get with a DFS. So that's DFS. DFS is intrinsically linked to this concept of a stack, because the stack kind of lets us keep track very carefully of where we've been and the order we were there. Right? So we want to backtrack as little as possible, which means that we don't want to dig down deep into that stack to try to find something else. And so this is DFS. I strongly encourage you to look up in the book an actual pseudocode implementation of DFS and familiarize yourself with how that works. This week's lectures will be a little bit shorter than usual to give you time to do that. So breadth first search, or BFS, is kind of the alternative approach here. And so what BFS says is, rather than walking away until I hit a dead end, I will do I'll enumerate the nodes in the graph in this methodical way. First I'll start somewhere, then I'll explore all the nodes that are one hop away from where I started. Then I'll explore all the nodes that are 2 hops away from where I started. Then I'll explore 3 hops, and so on. Right? So I'll spread out in an ever increasing number of hops away from the first node. Okay, so here's how this works. So explore all neighbors of start. Whoops. Of start. Then all 2 edges away. I should say 2 nodes away. Then all 3 nodes away. Dot, 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 and so on, right? And thus it continues. So here's how BFS works on this particular graph, and it ends up giving us a totally different traversal. So I'll do this traversal in blue. So if we start at A, so here's our BFS traversal, we start at A. What BFS does is it looks at all the neighbors of A and it goes to one that it hasn't visited yet. Once it goes to that one, it puts it into a queue. Okay, so again, let's break ties alphabetically, because why not? So A goes to B, and then it puts B, so now it has visited B, and it puts B in a queue. Okay, so what this means is that essentially we're gonna save this one for later, but go explore some other ones first. Okay, so we're gonna say we've been to B, so at some point, once we've exhausted everything that's close to A, B will be the first thing that we take care of, but let's exhaust everything that's close to A first. So after we go to B, then we go to the next thing alphabetically that's connected to A, right? And so what's the next thing that's connected to A? Well, it's D. So now we've visited D and we've enqueued D. So now D is sitting on our BFS queue, which means that after, right, so what is our queue now? Let's actually just write down the queue. our queue says B, and then D. Here, I should, yeah. So our queue says B and then D. And that's the list of nodes that we're going to go visit at when we get to them, right? So B and then D, but right now we're at A. And so we've just been to B and D, we've checked them, and now the next thing that is connected to A is E. So we'll go down to E. And so there we've just visited E. We've put E on our queue. And now we notice that we've visited everything that we can get to from A. So what we do next is we look at the front of the queue and we go to that node, right? We start exploring that node's neighbors is the better way to say it. So now we go to this node and start exploring its neighbors, right? We've already visited this node, right? But now is the time when we start to explore its neighbors. So now B has only one unvisited neighbor, right? The only unvisited neighbor that B has is F. So, So we are going to visit F next, and once we visit F, we enqueue it. Okay, so now F is visited. And so now what do? Well, B's neighbors are exhausted. We have no more neighbors from B that have not been visited, so now we'll go check D. D also has no unvisited neighbors, right? We've been to A. We've been to E, right? E is already in the queue, so we've been to E. So D has no unvisited neighbors, so we pull it off the queue, or we move the pointer forward in the queue, if you want to think of it that way. So now we look at E. We ask, does E have any unvisited neighbors? No, it doesn't. So now we go to F, and we say, does F have any unvisited neighbors? And sure enough, F has one, right? So then finally we draw that line to C. Okay, so just as an example of how these two algorithms operate, I've walked through them here on this simple graph. I've given you an example of, with an alphabetical tie-breaking rule, how DFS and BFS work, and I've prompted, at least very informally, how you use a stack or a queue to do the exploration here using these algorithms. So I want to think very briefly in the next video about how we'd think about the complexity of these algorithms. And then I'll let you go and study them on your own and do some practice traversals. There's plenty of practice problems in the book and online, just to familiarize yourself with how DFS and BFS work.